Okay, so in the previous video we invoked a put call parity condition that Quinru developed some C++ code for, and I just want to verify perhaps the veracity of this relationship. So what's being pointed out is that if we exchange S for K and R for Q, that transfer implies that the value of a put can be actually generated by using the call binomial tree. And we don't have in the code that we have here, we can only reasonably assert that we have code here for valuing an American put option. So how do we get the value of the put? We only have code for estimating call, should I say, S minus X or S minus K. How do we use that code to value put option? And the way that's generated is by using a result obtained, the put call parity result pointed out by MacDonald and Shroeder. Okay, these two authors, and that's paper it's not that old, 1998. Okay, so but very, very useful. Okay, so it's a very, very useful result, and basically it identifies that the time value of a call option, American call option, when is the current value of the underlying asset, K is the strike, gamma is the continuously compounded interest rate, and delta is the continuously compounded payout on the asset, so the dividend. T is the maturity or time to expiration. So in other words, if we know the value of a call, we can obtain the value of the put by switching S for K and lambda for delta. And of course the volatility is not going to change, or the time period is not going to change, but by transferring or switching S for K and the risk-free rate for dividend yield, we can estimate the value of the put by invoking the value to call. Both call and, define the time value of the put analogously for American puts. In this paper we proved that if the asset price is governed by geometric boundary motion, then this holds. Both call option and put options give the right to exchange one asset for another. For example, a call option on a stock gives the right to exchange cash for the stock, while a put option gives the right to exchange stock for cash. Given this similarity, we might expect call and put prices appropriately modified to be equal. This result makes precise the sense in which this is true. So we have the theory. Can we prove it then numerically, or illustrate that point numerically? I took a look at the Leisen reimer paper. This paper is 1995. It's a very useful paper, but useful in this context as well, in terms of both call and put prices for American options are reported. And I'll just bring up that table then to see those results and see if we can replicate some of the results. So what we have is the following. We have a strike price and value of the option for European calls, European puts, and American puts. Okay, so European calls, European puts, and American puts. We don't have, I presume there's no dividend. The dividend is set to 0 here. Okay, so that makes our job easy. We just look at the American puts and verify if we input these parameters into our model, where for the true value it's 15,000. Let me just check that. The true value here is given as 15,000 3 steps. So it's Cox-Ross-Rubinstein method using 15,000. Okay, so I'm going to take the American put option, use these parameters, and try a few of these exercise prices and verify the results can be replicated Okay, so for that purpose then we might line it up. Okay, so I'll just pause and line things up. Okay, so I'm going to take the results I have here. I'm going to copy them. I'm just going to copy our code. So try that one more time and copy and go into a new online C++ and paste these in, paste, and just verify that I have C++. Okay, so the code is, it's C++. Okay, and we reduce that. So if I run this code again, it's 15,000, I think. Yeah, I'll just pause for a second. Okay, so for the put option, using these parameters, 15,000 steps, I get 1772,416. That's the same value that I got before. And then if I change this to a call, just to verify, and the results obtained are consistent with the result I had here for Brody to Temple. I might just pause. Okay, and at 15,000 steps, the results I get for the call option is 9.0659, and that's the same as here, 44534, 44534. So, okay, so that's good for. Now we just want to verify that the results obtained for the put. Again, our issue here is I'm invoking MacDonald Shroeder put call parity relationship, and I want to verify with an actual set of results in a published paper. This is Leisen reimer 1995. We have Cox Ross Rubinstein in the final column. The true value is given as a Cox Ross Rubinstein and with 15,000 steps in the tree. So similar to Brody in the Temple, the same benchmark for accuracy. Okay, so what I need to change then is just I'll input these values into the parameters here, and I'll run the estimation for the put and then for the call. So I'll just pause. Okay, so the inputted values are the same here. So the S is equal to 100, R is equal to 7%, the time period is equal to 6 months. 6 months. There's no dividend yield, and the volatility I'm going to take as 30%. So we've got to change the 0.2 here to 0.3. Now, given that there's no dividend yield, the European call and the European call and the American call are the same. So whether I use A or E, I get the same result. But so I'm going to run this, and let's run. And we're going to have this try and verify that the value we obtain here using these parameters are consistent with the value here in the final column of 1013. 10.13377 in our estimation, and I'll just pause. Okay, so I was going to pause, but the values appeared, and it's 13.62. Okay, so relatively close. Not exactly the same. I'm kind of curious why it's not exactly the same. We'll just check here if we put in E that we get the same result. Okay, so we run. Now the results are very similar and only fractionally out. Again, this value here at 101336. Okay, same as before. So we get the same result as before. You can verify that again. Okay, so I'll copy this value here, just copy, and I'll paste for our purposes, paste, and I'll change E back to A, and A. Okay, so that should be capital A. Okay, let's run. And the value we obtain should be the same as this 1013,362 because there's no dividend yield in our estimation. Okay, so I'll pause. Okay, so the result I obtained here for the American option 1013,362,987 is the same result as here. Now, an interesting thing to note here, it takes 18 seconds to estimate the American option. If we change this to European, it'll be faster. Okay, so that's another important maybe detail worth considering. So this is for the American option, and it took 18 seconds. We're saying 18 seconds, and it was for the American option. When we put in for European, that would be faster. And I'll pause. And note, it only takes 4.25 seconds as opposed to 18 seconds. And that, in large part, is related to the fact that if we use the European algorithm, we don't have to select the maximum of the time value or the intrinsic. It's basically just time value, being a backward induction of time values. Okay, more about that later, but for the moment our results are approximately the same here. Now if we change the value to a put option, if we come back here and go to put, so make two changes. One, it's P, and the second one is, option style is going to be American, and the it's a put option. So when I run this estimation here using MacDonald Shroeder, the result I should obtain for the American put option should be the 7.035, given these parameters are consistent with these. It's 15,000 steps. It's S is equal to 100, K equal to, again, 100, and the same parameter values here are expressed here. Now, the last thing we might verify is just that if we change the option from being American to European, right, E, and then invert the comma again, and just run that again, it should be quite fast. And the result we get is 669, which is for the European put option with an exercise of 100 and the stock price or the underlying value being 100 and the same parameters. We get a value here of 669.4, and close enough. Now we could do one more here. We could change this value S or the exercise to a value of 80 and just, or 90 perhaps. Let's just try 90, 90, and execute again, run. And again, for a European option with a value of 90, we're getting 3.0412, so relatively close. And then for the American option, delete A, run. For the American option, the value we obtain is equal to, again, it'll take longer, but for the American option with 90 as the exercise, the value we should get for the put option should be 3.1233. Okay, and we're obtaining that value here. So it seems to work for both European calls, American calls, and European calls are going to be the same in this instance because dividend is equal to 0. And European put, European calls also, MacDonald Shroeder parity conditions also apply there for European and for American options. And again, the speed